Hello everyone, and welcome to the word ladder problem lecture. In this lecture we're going to learn about what the word ladder problem is. We're going to see how we can solve that problem with a graph. We're going to see an implementation of a solution in Python, and then we're going to begin thinking about graph traversal. A quick note on the implementation of a solution in Python: we're not actually going to live code anything out, because the main purpose of this lecture and the word ladder problem in general is just to get us thinking about how we can actually traverse through a graph and what kind of problems we can apply a graph to. So what is the word ladder problem? So consider the following puzzle. You have to transform the word fool, F-O-O-L, into the word sage, S-A-G-E. And in the word ladder puzzle, you must make a change occur gradually by only changing one letter at a time. At each step, you must transform one word into another word, and you're not allowed to transform a word into a non-word. So to give you an example, imagine you have fool here, which will transform into pool by only changing one letter. Then we can transform that into pole, and then pole again, pale, sail, and then sage. So at each step, we only change one letter, and we slowly transform fool into the word sage. So that's the basics of the word ladder problem. And what we want to know is that we can actually solve this problem using a graph algorithm. What we can do is represent the relationships between the words as a graph, and then use the graph algorithm known as breadth first search, which is what we want to begin thinking about, to find an efficient path from the starting word to the ending word. So what we want to do is figure out how to turn a large collection of words into a graph. And what we would like is to have an edge from one word to another if the two words are only different by a single letter. Then any path from one word to another is a solution to the word ladder puzzle. So let me show you what I mean by that. Imagine you have here this graph, and here we have fool, and here we have sage. And you'll notice that the actual edges connect one word to another only if they're removed by one letter. And what you should also notice is that this is an unweighted edge on all of them, and it's also an undirected graph. And remember, directed graphs are where edges only point in one direction. In this case, all the edges point in two directions, because you can jump from one word to another in both directions. Okay, so the edges are unweighted, and it's an undirected graph. So how could you actually build out this graph? There's several approaches. One approach you could do is take the assumption that you already have a list of words that are all the same length. So imagine you had all these words in the list, and they're all the same length, 4 letters. As a starting point, you can create a vertex in the graph for every word in the list. To figure out how to connect the words, you could compare each word in the list with every other. And then when you compare, what you're looking for is see how many letters are different. If the two words in question are different by only one letter, then you just create an edge between them in the graph. So that thinking might work for a very small set of words. It'll be fine. However, if you have a list of thousands of words, roughly speaking, you're going to have an order n squared algorithm, because you have to do a comparison from this word to every other word. So it's almost like a nested for loop. So you can actually do a lot better than that. And what you can do is suppose that you have a huge number of buckets, each of them with a 4-letter word on the outside, except that one of the letters in the label has been replaced by an underscore. So for example, as you can see in this figure, we might have a bucket labeled POP underscore. And as we process each word in our list, what we do is compare the word with each bucket using that underscore as a wildcard. So then both words like Pope and Pops would each match POP underscore. And every time you find the matching bucket, you put the word in that bucket. And once we have all the words in the appropriate buckets, we know that all the words in the bucket must be connected. So that's a way better and more efficient way of actually creating the graph we just saw versus the n squared algorithm we were thinking about, comparing each word to every other single word. This bucket solution with the blank is a lot better. So in Python, you can actually implement that scheme by just using a dictionary. The labels on the buckets we've just described are the keys to our dictionary, and then the value stored for that key is a list of words. Once we have the dictionary built, we can create the graph. We start our graph by creating a vertex for each word in the graph, and then we create edges between all the vertices we find for the words found under the same key in that dictionary, which is essentially that bucket. So let's go ahead and see the implementation in Python. Again, we won't live code anything out. We just want to begin to think about how we can build graphs to solve problems. So let's go ahead and jump to the code. So here we are now at the word ladder example problem notebook. Again, here I'm just actually on GitHub, not NBViewer, because we're not going to code anything out. I'm just going to go ahead and explore the code a bit so we can get a better understanding. So in order to construct the graph, I've just copied and pasted, and you can import this if you want, the vertex class that we created earlier, as well as the graph class. And this is what the build graph essentially code or function would look like in case you wanted to do this. So again, what you're doing here is the labels on those buckets we've just described earlier are the keys in our dictionary. And the value stored for that key is a list of words. Once we have the dictionary built, we can create the graph. And then you start our graph by creating a vertex for each word in the graph. So then we create edges between all the vertices we find for our words found under the same key. So in this case, we've opened a giant list of words. You said for line in the word file, go ahead and print the line and print the word if you're curious. You can just hashtag those out if there's too many words. Grab the word, and then say for I in range length of word, essentially just insert that underscore there, and then you're setting those as buckets, which are essentially your keys. Then you're saying for the bucket in that key, and then for the word in that bucket, again for word 2 in that bucket, if they don't equal each other, add an edge between word 1 and word 2. Alright, so again, you can check this out. I encourage you to go through it, but really, this is just to get us to think about how we can use a graph to solve real problems, and how we can traverse a graph. So in the next lecture, we're going to dive much deeper into how we can actually traverse a graph and search for something in a graph. Okay, thanks everyone, and I'll see you at the next lecture.